Okay, so they asked me to do a talk. They said I needed to be quick because the program was full. And it's basically a bit of a sort of a reproduction of some of the other talks I've given. So title, an Australian and New Zealand designed GPS receiver for Australian and New Zealand CubeSats and launchers. So this is the thing here. Okay, so I thought I'd start off with the most important stuff first, and then if I need to cut it short, I can. So basically, we've got a long heritage in doing this. We've been doing GPS here at the university since 2003, which is when I started my PhD part-time. The development is a bit of a kind of joint venture type thing between General Dynamics, I've written NZ there because it's not the General Dynamics, University New South Wales by the Australian Centre for Space Engineering Research and SnapLab, and myself. It's my one-man band company there. Okay, so we've got several GPS receivers that we're kind of pushing at the moment. This one's the latest one. It's the here B4.1 SB receiver, and that particular one is a Cal Poly compliant receiver. We also did a Boeing Colony 2 CubeSat compliant GPS receiver for DST Group, and that one got launched today as well, so very exciting there. The firmware is the thing that kind of makes ours different from your run-of-the-mill GPS receiver that you purchase, and basically it has to cover or operate in space, which most receivers don't, because there's all sorts of ITAR compliant things that you've got to comply with. You can't easily export them, and we've also done a bit of work on high-G acceleration type stuff, so you could actually put it on a rocket and do some launches, and I've got a simulation that we've run to show that it works with that. We've got two design-ins, so the key receivers on DST Group's Buccaneer Risk Mitigation Mission, and our own EC0 and USID's Inspire 2, and we're also flying the Nauru 3.2 on the DST Group, the ARI. Okay, so this is a bit of a history of some of the receivers we've done in the past. That's our first one over there, Nauru V1. This one was our main receiver for quite a long time, and when DST Group first came along to talk to us, we showed them that, and they said, oh, that's too big. So then we developed this one here. That's the one that got launched today. And this is our latest model. So the latest model is a lot smaller, credit card sized. The hardware design is developed by Kevin in New Zealand, and it's his company, and he's got his separate little company to do the marketing of it. So it's Kia GNSS Limited, and there's a web page at the end of the last slide that you can actually go and visit, and it's quite a nice web page. Credit card size, quite small. I've got one here. This is a real live working one. Small CubeSat sized. It uses a Smart Fusion 2 system on a chip. So that's got a little processor. It's a Cortex M3. There's big FPGA. That one's got 50,000 logic elements. Lots and lots of error detecting memory, so it can detect single errors and detect double error, single error correcting, double error detection. So serial flash for storing your almanac. This one uses Kevin's own custom RF chip, and it turns out that that chip is actually being tested for radiation, and it passed and worked very well. Okay, so as you can see, credit card size isn't Cal Poly compliant, so we've got separate little interface boards that we use to make it fit into the Cal Poly standard, and different customers could have different boards. So this particular one is the one we use for our own EC0 satellite, and this one has support for antenna switching. There's an extra serial port that you can connect up on USB to, and there's a big PC104 header that Matthew didn't think much of. Okay, the thing that makes our receiver what it is basically the firmware. So I developed the firmware, I've been working on this for quite a long time. It's fully licensed to UNSW, so they can use it and do whatever they want with it. Lots of features, but basically uses a small real-time operating system. It's recently been ported to FreeRTOS, which is a very widely used operating system. Has support for different RF front ends. Since in my past experience, I've found that it's quite a difficult job to move from one RF front end to another, so easy to do that. Lots and lots of features for doing the things that you care about in space. Most important ones down the bottom. Basically, when you go into orbit, you're moving very fast, so you need to do very deep frequency search because you're moving all the time, and the satellite visibility changes. You need to kind of take that into account. So there's a 2-line element propagator in there, so you can turn it on, looks at the time in real-time clock, works out what satellites are visible, picks the right satellite, predicts their Doppler, does all that for you. So it's all autonomous. And you can also do high dynamics, and we recently improved the sensitivity, so it's quite respectable. And we run that on Altera Neos 2 embedded processor type thing. It's a soft core, and of course the one that's on the Smart Fusion. Okay, so I've talked about the hardware, I've talked about the software. The last sort of leg in the tripod is the correlator stuff, and this was developed by the University of New South Wales. We've got 2 blocks of hardware. One of them is a correlator, and depending on how big your correlator or your FPGA is, you can have 11 or 12 or 16 channels. We usually have 11 or 12. That's the typical number for an L1 GPS receiver. We've had it running on Altera Cyclone devices. We've had it running on Microsemi Pro ASIC 3As or 3Es, and of course Smart Fusion 2. The way we set up our correlators is depending on the size. There's 3 code phase taps or 4, and they're half-bit spaced, so that's to do with the code tracking. We also have another thing which we're using for reflectometry, which is a delay Doppler mapped accelerator. And basically, it gives you the picture of correlation versus frequency. That's useful for doing reflectometry type stuff. Okay, so one of the difficult things about space is, of course, hard to actually go into space and test them. And one of the things that we've got here at the uni is a Spiro GPS simulator. Actually, we've got 2. We've got an old one and quite a new, recent top of the range one. And we test all our receivers on this simulator to make sure they all work in space. So we've got a couple of simulations we've done. One is just a standard orbit, low Earth orbit. And we've also got a rocket launch simulation. So the rocket launch simulation will take you all the way from the ground into orbit with 3 stages. Has 4G acceleration, it's got the staging, it's quite good. Okay, so these are some simulation results. Basically, this particular one shows you that the position errors are mostly within 10 meters, except right at the beginning when it's turning on. And this particular scenario has no ionospheric errors or anything like that. So that's just showing you how the dynamics work and how well the solution will converge. This side is the velocity errors, and they're always within half a meter per second. This is the timing solution, so we can do high precision timing when we're in space. And this basically says that the timing error is always within 40 nanoseconds in this particular scenario. So very, very accurate timing. Okay, last one, that's a rocket launch scenario. So we've got radial, along track, across track dimensions. This bit down the bottom is when the rocket's sitting on the ground, so that you don't really have any radial direction when you're doing that. Once you get going, you can see that it takes off. You get a few errors along the radial direction, bigger errors in the along track, which makes sense because you're accelerating up like that very fast, and cross track, hardly any errors at all. So working well and tracking the satellites as you're going up at 4G acceleration, and dealing with staging, as you expect. All right, so I've scraped within the 10 minutes. Yep.
We've even got time for questions.
That's right. So basically, the takeaway is, yes, we do have a GPS receiver. We've developed it here. It's homegrown. It works well. It's got a good long heritage. We can customize the design for particular applications, as we've done. There's some email addresses there if you want to talk to us. That's the web page for Kevin's Kia GNSS web page. Worth a look. And if you've got any questions, you can chat to me in the tea break, or you can send us an email. Done. Within the 10 minutes.